In this video, we are going to walk through the process on how to impose a design constraint on element force if you're performing a frequency response analysis. If you've seen the few videos before this, we are using the same example from those videos, a simple spring mass system that you see on the right. Quick call out. If you have questions, comments, feedback on how to make these videos more useful to you, if you want access to more advanced training, if you want my guidance on a project of your own, if you want access to the web app I use today that makes it really simple to perform your optimization, reach out to me at this email address and I'll definitely get back to you. So now here on the right is what our initial design's frequency response result looks like, specifically for the spring force. We can see that at a forcing frequency of 0 Hertz, we have a spring force of 100. And at a forcing frequency of 3 Hertz, we have about a spring force of 900 newtons here, as you can see me highlight. The question we're looking to answer is, what value of the stiffness of the spring will produce a maximum spring force of 700 newtons? So that, in effect, we're trying to minimize the maximum spring force that you see here from 900 newtons to 700 newtons. Here in blue is what our final design is. Feel free to pause the video here and glance over the description of the model. And now as for your optimization problem statement, the objective is to minimize the cost of the spring. This is associated with the stiffness of the spring. The stiffer the spring is, the more costly the spring is. The less costly the spring, the less stiff the spring is. We'll allow the stiffness of the spring to vary, and this will be our design variable. And our design constraint, what we are going to do is, for all the forcing frequencies, we want to make sure that at no forcing frequency should the spring force be more than 700 Hertz. So now let's go ahead and walk you through the process on how to do that for MSC Nastran. So let me move this to the right and let me go ahead and open. Let's go to the web app and click on Design Constraints. Let's switch the analysis type to Direct Frequency Response Analysis. And we'll search through the list and we'll look for the one that says Element Force. Click on that one time to create one constraint. And this table is where I can configure my constraint for the element force. First, let's adjust our upper bound. We are saying that the maximum spring force should be no more than 700 newtons. So I can simply type in the 700 there. And now for the other ones, this is where I have to refer to the MSC Nastran quick reference guide, and I'll do that in a moment. For property type, this is the property of the spring, which is a P-bush. And the corresponding ID or PID for the P-bush is 1. For the force item code, this is available in the MSC Nastran quick reference guide. So let's jump to that manual right now, and we'll look for the section called Element Forces. The element force table has all the item codes for each element, and right now I want to track down the one that's associated with the C-bush element type. So I'm going to keep scrolling down until I find the index of item codes for the element forces. I'm in that section. Scroll down until I find C-bush. Perfect. So I want to know what the element force is in the X direction. So I would use an an item code 2 in this case. So let me go back to the web app. I'll type in an item code of 2. So again, we are constraining the element force, hence the item code 2, for P-bush 1. So any element associated with P-bush 1 will be constrained. And we are saying that the upper limit is 700 newtons. This box has various meanings. As I demonstrated in a previous video, you can use max, you can use min, you can use RSS, RS, or SSQ. But if you leave the box blank, that will then constrain every single point. So let me explain what that means actually. Prior to your frequency response analysis, you specify which forcing frequencies to perform the analysis on. So here we perform the analysis on a forcing frequency of 0 Hz, 0.25 Hz, 0.75 Hz, and so on and so on. By leaving that box blank, it's going to constrain each individual point. And this is exactly what we want. So now let's go ahead and copy the output from the web app. And we'll put this back in my design model. We'll save my design model, and now we'll perform my optimization. If any of this is new to you, I definitely encourage you to view the dozens of videos on my channel that walk you step by step on how to perform an optimization on your own. And they really range from topic to topic. Also, this web app is available if you contact me. So my email address was at the beginning of the video, so feel free to reach out to me for that. And let's go ahead and inspect the results here. And let me compare what I plan to get with what I actually got. Okay, perfect. So here our summary of the objective. We see that we started with the spring price of $10 and we ended at a spring price of $10.35. The spring stiffness started at 2000 newtons per meter and actually landed at a spring stiffness of 2071 newtons per meter. And this will be the same result in my PowerPoint, which is what I expected. So let's look at the final plot, if you will. You can see that every point is under the 700 Newton constraint. Even the last point at a forcing frequency of 3 Hertz is under my constraint of 700 Newtons. And this was my intent. And this pretty much concludes how to do or impose a constraint on element force if you're performing a frequency response analysis. If you want me to guide you on performing an optimization of your own for MSC Nastran, definitely reach out to me and I'll be more than glad to have a discussion with you. Thank you for watching.